This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, I think we can start. I think this is where we left last time. We were talking about training of neural networks. Maybe an announcement before we start regarding the workshops. The report will be due end of this week, and then probably Sunday night, and then the next week, the last workshop, I will post it probably tomorrow, and then that will be on reinforcement learning. And then you will have 2 weeks. That will be also a short one like this. So the 2 weeks workshop. And actually that's the normal size, 2 weeks is standard size. And then we finish the semester essentially. And then we will have SWOT-WAC and consultations for the final exam. The final exam dates are released, right? So it's the end of June, so there's a bunch of time to catch up actually. So I have discussed the backpropagation, with math part and a nice demonstration people have prepared online. So we have gone over that. The next step is talking a little bit about regularization in neural network training. So this is the same story as we discussed before. So same regularization concepts and methods. Slightly additional stuff too, but the fundamental idea is the same, right? So we have the input and output dictated by data. How we train the neural network, we use the supervised data. And for a feed-forward neural network of the setup that I've been discussing, that's more specifically. And while you're training it, we pose it as an optimization problem. I mentioned it. Then you use the gradient algorithm to solve, to find the weights of the neural network once you decide on an architecture structure with the number of layers and parameters. And just like before, you can actually regularize this learning process and optimization problem. So in deciding the architecture of the neural network, we make a lot of decisions, right? The number of hidden units, that's the classical one if you choose a single layer, classic feed-forward. But also, in a modern deep learning setting, deep neural network, you need to decide on the number of layers. You need to decide on the activation functions for each layer, the output layer, and then the intermediate ones. ReLU is pretty popular these days. And then the number of hidden units in each layer, right? And then the number of weights is proportional, of course, to the number of hidden units, one-to-one relationship there. So what would be the number of hidden units that gives the best generalizing performance? And that's again, goes back to the trade-off between overfitting and underfitting, right? So I've put this figure just as a representative figure, but like this would be kind of an okay model, but then you get a lot of bias errors. Here, this is an even better model. This is obviously an overfit, right? So striking the balance in the model selection is kind of a complicated problem. I don't have time to go into detail, but I put the link here about model selection literature. So you can use actually information theoretic metrics to help you select a model. So that is possible, and people have worked on it. So you can evaluate different architectures that make sense to you, and then evaluate their infotheoretic properties, which kind of gives you kind of a clue to find the nice middle between underfitting and overfitting, right? So it is a bit of an art because it is a design process. So you are designing a structure, essentially. There is no kind of a linear This is not a linear process. It requires a little bit of creativity, a little bit of ingenuity when you choose the architecture. But it can be done, and then there are methods to help with that. The next slide is giving additional clues, right? So we know that universal approximation theorem works for a single hidden layer network, but then you need, theoretically, you need up to infinity, too many hidden units in that single layer. And the theory is one thing, practically training it and getting good results is another thing. And people, this is a very practical field, experimental field. When I say practical, it's very experimental. So people have done tons of experiments, and deep learning book keeps talking about those experiments. And then experimentally, people have realized more layers, even though you have the same number of hidden units, instead of putting them to one layer, to a single layer, hidden layer in a linear case, you can actually create multiple layers with the same number of hidden units. And people realized with experiments that this works better for a variety of tasks, right? So these figures kind of show it. The depth, number of layers versus the accuracy increase, and then the advantage of having a bit more layers is even with the same number of parameters. In the x-axis, you see the number of parameters here in the bottom figure, and then the test accuracy on the test set accuracy on the y-axis. So even for the same number of parameters, you get better results if you add more layers. Like instead of 3 layers, you put more layers for different types of networks. On the other hand, if you go to the right, as you increase the number of parameters, the performance increases up to a certain point, and then as we expect, it starts to decrease because you're getting to the overfitting region. So you increase the model complexity by adding more and more hidden units, even though you keep the number of layers the same. Or you see the performance on the test set decreases. Of course, performance on the training set will improve because you're definitely overfitting. But then on the test set, so if you do this on the training set, you're not generalizing well enough. On the test set, things will mess up. Right? And I think that's something you should observe in the workshop 3 as well with the neural networks. I think the tasks I have given you will give you that opportunity to observe it yourself. Any questions regarding that?
Sorry.
Yep.
Can you explain more about the legend of this graph, like convolutional?
The convolutional nets I haven't discussed yet. Those are CNNs, convolutional neural networks. I will discuss today or latest tomorrow. The fully connected ones are the feed-forward ones. So they are also known as dense or fully connected. Those are the regular feed-forward networks. Then there's the convolutional networks and the LSTMs, and then I'll discuss those. So you see the same concept of when we were doing regression, overfitting, underfitting, with respect to number of parameters or the polynomial complexity, it translates directly to the neural networks as well. Yep.
So the parameters, number of parameters is basically how many nodes in a single layer?
Or single layer or multiple layers, how many nodes. And then this graph shows both. The bottom graph shows on the x-axis is the number of parameters. Of course, as you add more layers, you also increase the number of parameters. But you can also, make it like a single line, single hidden unit. Let's say you have 10 parameters in the single unit. You can convert it to 4, 3, 3, right? In the 3-layer network. I'm just giving a toy example, but you can take a single layer network and convert it to multi-layers, obviously, and then people have observed that it works. I will actually touch this. It works for wide variety of tasks. There is this theorem of no free lunch. I will come to it today. The fact that you do well on certain tasks doesn't mean you will do bad. You will do as always well in other tasks. It's a very interesting result. But what we care about as engineers is solving certain class of problems. And if it works for a certain class of problems, we are happy if you achieve your goal. It may not be a universal result. This is not a theoretical universal result. The only theoretical universal result is valid for even a single hidden layer network. Universal approximation theorem. The universal approximation theorem and property of the neural networks. But I don't think there exists a mathematical theory that precisely establishes this as a fact that, multiple layers work better. There is no theorem like that. Only experience. And then, as I was saying, this is a very experimental field. It's a very, very practical. When I say practical, it's very experimental. So regularization in training neural networks, as we will see soon, maybe I should have put that graph earlier, the optimization problem when you train the neural network looks like this, so I should maybe move forward. This is the landscape that you're optimizing. It's a very, non-convex optimization problem. It's very, very non-convex, very high dimensional, very non-convex problem, and lot of local minima, a lot of valleys, and then you are trying to do your best from a random starting point, find the bottom of one of those, right? So it is a complex problem, and in complex problems like these, it is very easy to overfit and get stuck in a local minimum. So regularization actually helps with that. So people have come up with different regularization methods, and let's discuss these a little bit. And the regularization method, some of them you already know, which is adding an additional, objective, balancing the original objective and some normalization factor. And then there is a hyperparameter balancing the original objective and then this regularization objective. And what type of regularization we have? The ones that we have know from before also apply to the neural networks. Like you can do L2 regularization or ridge regression. You can do that directly. And then the software packages also give you that option. So you see here it's an L2 quadratic regularization factor added to the original objective that I need to minimize in order to find the weights, right? So I put a regularization, L2 regularization, quadratic regularization in terms of the weights here, and balance them with an alpha. Of course, I shouldn't do alpha too much, because if alpha is infinite, then I ignore the original factor. If alpha is 0, I ignore the regularization. Then alpha is my knob to turn, find the balance between the two. Or I can do L1 regularization, which is the L1 norm. That will be the sum of the absolute values of the weights, and that term promotes sparsity, as we discussed before. So if you want to promote sparsity, that actually is a good idea. Why? Because if I create a big neural network and if some of the weights are 0, then those matrix multiplications become sparse matrix multiplications that can be implemented also computationally much more efficiently, and I end up learning less parameters. So that improves generalization, right? That decreases the model complexity, in a sense. So regularization helps. This also helps, is suitable for feature selection. If you are doing a neural network to select features and zero out some weights, that will give you more condensed features like we were doing in PCA. So we start with a huge feature vector and map it to a smaller one. So sparsity can be also used for feature selection like that. So so all we do is we take the optimization objective that we use to find the weights of the neural network and regularize it. Another method, these are the two methods that we have done even back in classical regression. So the same idea applies to neural networks directly, because we have a similar optimization process here as well. There is another regularization approach. We can actually put it as a constraint. I was talking about this when I was discussing the optimization, right? Multi-objective optimization. One option is you can create a weighted, if you have multiple objectives, the one classical option is you put them together in the objective function and put a weight parameter, trading them off like the alpha, as we were doing here. So one objective is this, the other objective is that. then alpha balances them, then the weight of this is 1 fixed, or you can do alpha and 1 minus alpha, really doing a balance between two objectives, shifting the weight from one to the other. So if you have two objectives, you can do this. Or actually, I was saying you can take the second objective and make a constraint out of it to ensure that that second objective achieves at least a certain level. And that could be, you can put a norm penalty as a constraint. You can take the this regularization objective and say that that should be at least k or less than or equal to k. And then that makes it a hard constraint problem together with the original objective function, mean j, subject to this constraint. And I can write the Lagrangian, and once you write the Lagrangian, things look quite similar actually. And then you can solve for alpha star and theta star, so that this dictates not only then, if you put it as a hard constraint, it dictates not only a solution, the optimal weights or the parameter vector theta in this case, but also the optimal weight. The weight comes down from the hard constraints, right? In the other case, you are balancing the weight, you make a previous choice. Here, your pre-solution choice is not alpha, but you are choosing the constraint itself, k. Right-hand side of the constraint is this choice you are making before solving the optimization. In the other case, you are explicitly choosing alpha before optimizing. So it is roughly the same thing, actually, if at the end of the day, once you write the Lagrangian, they as you can see, the picture is quite similar. Only thing that you decide is the minimum or maximum of the constraint beforehand versus create a weighted sum and then decide on the weight balances the two objectives. So this is another regularization method. Then other approaches to improve things, to prevent overfitting, which is as I was saying an easy problem in neural networks, is dataset augmentation. As we have discussed before, if you have more data, then you kind of, this remedies the overfitting problem. We were discussing that in the regression. If you go back to your slides, the more data do you have, the less the danger of overfitting. But if you have a fixed data set, what are you going to do, right? So one option is, and this is not an ideal option, is generating additional data based on the training set. So essentially, you create synthetic data based on the training set, augment the data set, your data set. In some cases, it might be easy to do. In some cases, it might be impossible. So making up things is not a good idea. For example, it's almost impossible in density estimation, because if you don't know the density of the characteristic of the data set, how are you going to generate samples that are similar, right? Because that's what you are trying to achieve anyway. It's a circular issue here. If you are trying to do density estimation like a Gaussian mixture model, you cannot actually augment the data set, because then you will be deceiving yourself. In some cases, like classification, maybe you can actually make some density estimation first, generate a bit more data, and then use that generated data and to prevent overfitting. It's not an ideal method. Why? Because you are making things up, right? So this is not a good idea. So the data is real. That's the best thing about this field. So the data is real. That comes from the real world. The moment you start to generate stuff yourself, you are departing from reality, right? So, and then you are making a lot of assumptions. And then you may or may not hit back the reality or deviate from it and get nonsensical results or worse results. Even though the methodology may look nice on the paper, your end result may deviate from reality, and then you fail in the original goal. And this is the quite standard early stopping, like when you train the network, as time passes and passes, you can actually get better and better with the loss, but the validation set loss, so this is the loss is the objective function that I'm trying to minimize, which is negative log likelihood, that log likelihood that I'm trying to maximize on the y-axis, and x-axis is the training iterations over the whole data or instances, and then the training set loss will get better and better as I spend more time and more time. Even for a non-convex optimization problem, I should not do worse. But then in the validations, if I start to overfit in the validation set, I may get slightly worse results. You see, it starts to bottom here, but starts to go up from after a point. So you spend time, but it's unnecessarily spent. So that's not that good. And other two are bagging and ensemble methods. I don't have time. Ensemble methods are actually quite important, but I didn't have time to go through in the machine learning part. The idea is quite simple. Train several different models, then combine them. Right? That means more work, but if the models vote on the output for the test examples, it usually works pretty well. Actually, in classification, it is well known that if you train multiple weak classifiers, even though that by which I mean individual classifiers that are not so good, but then you combine many of them, you get pretty good results. So it's kind of wisdom of crowds type of thing. So each weak classifier that you train doesn't do well alone, but together, if you you need to also train how they vote together. So there's a weighting optimization there too. So when you combine, you can combine all of them, giving them the same weight, or you can do a weighted sum of their output. What are those weights? It needs to be, again, trained based on the training set, and it's a supervised learning problem in itself, and there are algorithms like AdaBoost that do boosting, and AdaBoost's most famous example, which kind of helps you training those weights when you combine individual learners. So this also requires, even though they are weak learners, you still train many learners. That's computationally quite expensive compared to a single one. Any questions? So just that we are not getting lost, what we are talking about is regularization. What's the purpose? We want to prevent overfitting. Where does the overfitting come? We may end up putting too many layers, too many parameters, and then when we train them with a very non-convex function that we've been talking about, you may end up overfitting easily. So we don't want to do that, overfitting on the test set, training set, and we want to avoid that, and we want to generalize nicely. This is especially true when you think about most of the deep neural networks have tons of parameters. When you put a few layers, also you noticed, I think I make you look at the number of parameters. You have tons of parameters when you put even a simple deep neural network. And compared to the data set size, you may end up putting too many parameters. So the regularization is very crucial for the deep neural networks to be successful, because you cannot afford to overfit, as we know. The final thing is dropouts. So if you put a big neural network, that's very expressive, right? You have a complicated model. Complicated models can do good things if they are kind of tamed and trained well. You may want to drop some of that complication out of the picture. So you still want to have maybe multi-layer model with a lot of units, but then you say, okay, this is too much, this will overfit, I'm afraid. Another option you have is dropout. So you kind of drop out randomly some of the hidden nodes and create a bit sparser network. This is the toyest example, very simple example, this picture. So you have 2 inputs, 2 hidden nodes, and 1 output, right? Very, very toy example. Imagine this, compare this to what you have been doing in the workshop these days. If you randomly remove things, there's also danger that you remove the inputs, which is not that good. Also, there's a danger of you may end up with a nonsensical network if you do a random dropout. Like this is nonsensical, nothing is connected. So you kind of ignore it, and then if you look at this, there is no input, so that's also nonsensical. If you have for this small network, when you remove things, it's very easy to become nonsensical, obviously. But if you have a big network, you randomly remove some 10%, 20% of the nodes. Usually you don't end up with nonsensical, but things like these, you see, or this one with less number of hidden nodes, randomly selected, and then you try to see how it goes with that. So because you decrease the model complexity by removing nodes, obviously. That removes the number of parameters, reduces the number of parameters. So as I was saying, in larger neural networks, most subnetworks will be connected and useful, whereas most of these actually here are either nonsensical or not terribly useful because you ignore some inputs. That's also not very useful. All right? So the regularization, maybe I should have put this regularization after the optimization for training. It's kind of, I was following the flow of the neural deep learning book. So we could have discussed after the optimization because regularization is closely related to the optimization methodology, but it's also, maybe it's okay because it's architectural methods like dropout, like the early stopping, dataset augmentation, and then the changing the cost parameter. These are independent of the optimization methods that you use. So maybe it's okay. So these are more like model selection related issues because your cost function is part of your model too in a larger sense. So once we have these architectural and model-based methods that are helping me doing not overfitting and underfitting, the next step is how do we do the optimization for deep neural networks? And we discussed the backpropagation. That is the classical training method for neural networks. And all of it is based on the backpropagation, but backpropagation gives you the gradients that you need. The popular these days, as of 2019, almost all of the deep neural network methods are based on gradients. So you will need the gradients, you will need backpropagation to find the gradients, but that's not the whole story. So you can use gradients, as we were discussing, in different ways, right? I mean, there's the Newton method that we did, there's the gradient method, and then there are many, many variants that now we will discuss in a bit more detail, right? So let's look at these in a bit closely. But any other questions before I go there to the optimization? So this optimization actually part builds upon our knowledge. Essentially, these are variants of gradient methods, but it's also more sophisticated, to be honest. Actually, this is going to the direction of stochastic optimization, non-convex optimization. It builds upon the fundamentals of convex optimization you have learned, but it is a bit also more sophisticated. So, therefore, yeah, it is not as trivial as what we have discussed, as I was trying to say. So let's see. One interesting difference between general optimization and the machine learning algorithms, like also the neural network optimization, is the objective function decomposes as a sum of training data points, right? So here, for example, is a maximum likelihood. So what we have here is the argmax of the sum over the data points, log, it's a log likelihood, right, over the data point, and then I sum it over the data points. And the gradient, if I want to do the maximum likelihood of the parameters, these parameters could be the weights of the neural networks, to be clear, right? In the context of neural network, these parameters include the neural network weights, and especially they are the neural network weights, so this theta. So you sum over the data points as a expectation, expectation as a practical estimator for expectation, or practical estimation for the mean, right? Expected value of the log p would be then this. So this is the problem I want to solve at the end of the day. The task is easy to express. Where does the sum come from? Actually, maybe just before people ask me many times, so maybe I can create, I haven't created the notes for this way, this one. Let's create some nice notes here. So just this will come up again today. Therefore, it's kind of worth mentioning. So if you take an expected, why is it green? I don't know. So if you want to take an expectation of a f of x, for example, where x is a random variable and f of x is a function of a random variable, the empirical mean would be then the empirical mean. For example, if you have a data set, or data set, x is x1 to x1 vector to xn vector, a data set of size n. What would be the empirical mean? Empirical mean would be then 1 over m, n, in this case, capital N, sum over I equals 1 to n, f of xi, right? So these are the data set that you assume comes from the, if you adopt a probabilistic point of view, you can say there is a x and the probability of x, from probability perspective, you can think of an x as a p of x distribution, and that generates IID, your data set, right? That's kind of the thing that we were talking about, the probabilistic view of the world. You say, oh, this x random variable has a probability distribution p of x, and then that generates through an IID process my data set. And in reality, you only have the data set. You never can double check whether there is a p of x. You can only estimate it, right? So there's this reality gap between the kind of platonic p of x and reality of the data set x. What you can do, the best you can do is you can take the data set and find the empirical mean as an estimator. So this empirical mean is an unbiased estimator of expectation of f of x, right? So that's the story, and then f of x could be then this loss function. So maybe I could have, so then note that f f can be a loss, right, function, or log likelihood, etc., right? So it can be anything, but the loss function can be loss function, which is example, for example, it could be log likelihood. Now, with this mindset, I have a probabilistic model, but the practical implication is I have only data set to play with. So I use the probability to think, and then data set to compute. Yeah, maybe that's a good summary of the situation. I use the probability to think about things, and then computation to compute things, the data set to compute things. So then you can drop the 1 over m because it's an optimization problem. So you get this sum. And when you want to optimize this with a gradient method, what do you need to do? You take the gradient of the objective function, right? So when you take the gradient with respect to theta, that's the backpropagation kind of, right? You get the expectation over x and y, x and y is the label here, that comes from the empirical data set's probability estimation, because I don't know what creates the data set, but I can make a density estimation of the data set. So, and then that would be my expectation, taking the mean, and then the mean of the gradient of individual, elements. So, and then the empirical estimation of this expectation is this, essentially. The problem is, if you use the entire data set to estimate this gradient, you're in a bit of a trouble. The data set can be pretty large. Big data was the buzzword at some point, right? So you may have a substantial data set, it can be very expensive to compute because it requires evaluating the model on every example in the entire data, entire data set. And when you do the iteration over theta and iteration theta t plus 1, theta t plus alpha times the gradient. So you need to do this gradient estimation many, many times because this function is depending on the data points, but also the theta itself. So you have this, you need to do this again. So what we do is we can compute these expectation, gradient estimation essentially by randomly sampling a small number of examples from the data set. So we don't use the whole data set, we use a small subset of the data set and taking the average over only those examples, essentially. So that's the whole mini batch business that you have been doing, right? So you're not using the whole thing, but a subset of the thing. This is an important aspect, so I would like you to be kind of clear on it. So the next slide is maybe a bit more explanatory, if it works. Oh, great, computer is frozen. Oh, the keyboard is frozen. Okay, that's fine. Anyhow, so we got adopting this probabilistic approach, as I mentioned, the optimization objective, this expectation that we do with the empirical data, we say that it approximates this Platonic original data generating probability underlying, which we will never know in most cases. So we kind of, this is the best we can do in real life, which is fine. Then this is, then L is inside this, essentially inside the sum, is the per example loss function, right? And F is the prediction function. If I'm doing a regression with my neural network, so F could be a neural network actually. F of x theta will be x will be the input, theta will be the weights of the neural network, and F is the function that represents the neural network like we have done before, right? So, and Y will be then the output. So this is the loss function, output of the neural network, and the Y is the label or output of the supervised learning. And then you have the loss function of the two. So that is the big view that I've been talking about. And because we don't have the real probability distribution, we have to work with the empirical, and then this expectation is, empirically estimated, as I was talking about, with the empirical mean. I gave the general case in the note just 1 minute ago, right? Now this is the specific case for the loss functions, a bit more specified, the loss function between the model and the output, and then the model could be a neural network as well, but this is also general for any machine learning algorithm. So you have this, empirical mean that we use, and then 1 over m when you maximize doesn't make a difference. Therefore, you can drop it because we have the number of data points is a fixed given. So we have the sum that we have seen, right? So this is also known as empirical risk minimization. And practically, as I've said, in neural networks especially, you cannot, when you take the derivative of this, when you do the derivative estimation, you don't use the whole data set, but you use a subsample of the data set in order to decrease the computation. Otherwise, you can use the whole data set, right? I will come back to this. But this empirical risk minimization business, do you understand what's going on, or are there any questions to clarify it? Everyone lost, or is it so clear that everybody's happy? Well, some people say half-half. Yeah, maybe once you read it again, or maybe when we do this example. So we have an example to do. I think it's definitely worth doing, and let's look at that. So we can. This is a very funny question. It's a very long text, and the answer is very short. So sometimes you have that. Sometimes you have very simple questions and very long answers. Like there is these famous theorems, like Fermat's last theorem that comes to my mind from math. Like it is very simple to express, and then the proof is like 200 pages. And then this is the opposite. Like sometimes it takes forever to explain the problem, but once you explain it, the answer is trivially simple. So this is one of those. Let's do it. Let's go over it together. This is from Boyd's book. So this is kind of also interesting. So Boyd's book looks at things from purely optimization perspective, but we will connect it to the machine learning directly. So you can see different perspectives merge or meet in the middle sometimes. So in some optimization, this is also directly related to robust optimization. So we have some optimization problems. There is uncertainty, right, that are beyond our control. So we can actually make the function our optimization formulation a function of those unknowns. So you have the minimized f0 of x subject to f. We were using g and h, but Boyd's book uses f1 to fn for inequality constraints. So if you write everything in terms of x, that's the canonical form of a regular optimization problem. But then if we take into account these unknowns as a parameter vector u, so then the u will be done as a random variable with an unknown distribution, and then we need to take the expected values over this. So then I write these unknown u's into the problem, but because u's are random variables, what does it mean to optimize? The original optimization problem is deterministic. There was no randomness. Once I put u's in it, random variables, actually it becomes a stochastic optimization problem. And then that's the stochastic optimization formulation. You can actually bring it back to deterministic pretty quickly by taking expectation. That's one way to bring it back, right? So that would be then, we can work with the expected values with respect to u. And then there is also, that's not the only way coming back to deterministic. You can also do a worst case analysis. Then you take here as discussed, you take the fi xu, and then you look at the worst case values. If you want to minimize, then the worst case values, you find the max over u. What's the worst that can happen, right? So, and then here to simplify, there are no equality constraints, but you can write it for equality constraints as well. So I will just focus on the expected values, not the worst case scenario optimization. But if I write in the worst case values, the expected values like this, the problem first asks us to show that if it's a convex optimization problem, so objective and the constraints are convex, then it's a convex optimization problem. Can we show that this stochastic optimization problem that I formulated through the expectation of these unknowns u, is it also convex? So that is interesting, and the answer is actually yes. Can we show? Yes, we can show it. And then let's do it pretty quickly. So let me put it here, the bunch of text. But then how can what was the fundamental definition of convexity? I can write all of the fi from f0, which is the objective, and then the f1 to fn, m, the inequality constraints. For each fi, if I write it this way, the condition for convexity, then it would be, write it this way, fi, right? So I can write it as maybe alpha x plus 1 minus alpha y, and then it should be less than or equal to the line above it, alpha f of x. Actually, this is with u, so this is the difference. This is this, and then there's uncertainty, and then I have alpha f of xu plus 1 minus alpha f of yu, right? So this is the line above, and if it's convex, the function value is less than or equal to the line above. And the question is, when we write it in this way, essentially all the functions, I take the expectation with respect to u. If I take the expectation, then if I write the expectation to both sides, expectation, so this would be the expected value, and then on the right-hand side, what will I have? I will have, because expectations is a linear operator, I will have E alpha expected f of xu and 1 minus alpha expected f of yu. But then I can write everything in terms of the expectation, which is the case for the formulation we have. So the convexity condition holds when I take expectation. Therefore, the formulation, the optimization problem is convex. So that's this one. So the optimization problem is convex. When I take the expectation, nothing changes, everything remains convex. That's still a convex optimization problem. So as I was saying, this is a pretty straightforward in terms of the the answer. So the connection to this is, there is actually a connection, maybe we should say that as well, there is a connection to empirical maximization as we discussed. So it would be then expectation of the loss function with respect to theta and xy. So these are the data points. If I write this, then that would be the same as 1 over m as we were discussing, I equals 1. And I was writing it, and then that would be then L theta xi yi pairs, right? So then there is this connection between this stochastic optimization formulation and the formulation we were discussing. So finally, again, there's a simple finite set of possible parameters values. Actually, I have already answered this by writing that. So when we have the FIXU, so we have this, but then we are giving set of possible values of the parameter is finite. So you see this is like the data set of the U1 to UN. And then instead of estimating the instead of having the probability distribution over U, we have the data set, and then we can write the probability. We can set up the stochastic optimization problem explicitly in terms of the expectation over the U. How can I do that? I can do it this way. So there is this connection, and then actually the whole story is as we have discussed. Then the stochastic formulation would be then probabilistic version would be then the mean sum over k pk f0 of x uk, and then subject to sum over again k pk fi of x uk less than or equal to 0, right? So I equals 1 to m. So I can actually write it as a stochastic optimization problem. Here the probabilities are explicitly assumed, so pk is the probability of the u, right? So p of u given, if p of u is given. But if it's not given, then I do an empirical mean, and empirical mean looks like what I've written before. So this is the stochastic formulation if the probability is known. So it's again a bit of a theoretical case. All right, so I thought this is clarifying things a little bit, or exemplifying, connecting to the literature from optimization. And in practical terms, maybe this is the slide that we need to do before giving a break. So what does it mean practically, and then what you have been doing in the workshop as well? So if you train over the whole data set, then this was traditionally called a batch, right? So you have a data set, and then most of the algorithms we talk about uses the entire data set in machine learning, like support vector machines. So you use the entire data set to solve the quadratic program to find the boundary, right? So you use the whole batch of it. In neural network training, if it is the name is actually, the deep learning book calls this still a batch and then admits that it's confusing. The practical methods, everywhere on the web, people call it an epoch. So if you go through the entire data set once, that's an epoch, right? And then the classical name for it is a batch. Therefore, because the classical name was a batch, a mini batch is this random subset of the data set. I was talking about this, right? So when you do the gradient estimations, you don't use the entire data set to estimate the gradient in your gradient methods, but you are using the random subset of the data set. But because this is called epoch collegially overall by the community, then community calls this as a batch and then talks about the batch size, right? Batch size is the number of samples within this mini batch. So I put the mini into parentheses. If you call the whole data set batch, then you have to call this as a mini batch, which is kind of meaningful, but because no one calls the whole data set batch, everyone calls it an epoch, they don't call it mini batch, they call it batch. The batch size in your libraries is the mini batch size actually. And then what do you have? If the mini batch, for example, if your data set is 100 and mini batch, then one epoch means going over 100 data points. Then batch size 10 means there are 10 batches in a data set of 100. Make sense? So that's for example, Keras uses that. And then iterations is the number of batches needed to complete an epoch. So if your data set is 100, then to complete an epoch, if your batch size is 10, you need 10 iterations. Right? 10 iterations gives you one epoch. Okay, so it's very simple. There's nothing going on here, just the terminology. So I tried to clarify this. I hope this makes it a bit clearer, because as I was saying, the deep learning book calls the epoch a batch, and then says, "Oh, this is confusing." I think they felt compelled because of the prior literature. Why do we need the mini batches? The reason is we use the mini batches to estimate the gradient, and I don't want to use the whole batch, the whole data set to estimate the gradient. Therefore, I use a smaller mini batch as a random subset. So, if we look back, the classical machine learning algorithms we discussed earlier, like the regression or support vector machines, other type of probabilistic regression methods, they were all batch methods, right? With a single iteration and single epoch, right? Because there was no mini batch, the whole thing is used you go through the whole data, and then you do it in single run. There is no multiple run. But when we train the neural network, usually we go, because we are doing an approximation by subsampling, and then we do the iteration through the subsampling, we often go through multiple epochs, right? So multiple iterations. We go over the data set a few times over and over again. So when we do that, so the batch size is an important meta parameter when you train a neural network. So larger batches obviously provide a more accurate estimate of the gradient, because we have discussed this. The gradient estimation is an empirical estimator, unbiased empirical estimator, but of course, as you increase the size, you get better idea of the gradient, but that's computationally costly. So small batches are making a mistake, so they don't give you the perfect estimate of the gradient, but that can have paradoxically can have an advantage, because they are doing a noisy estimate of the gradient. When you have a small batch size, you get a very noisy estimate. The smaller you make, the noisier your estimate gets. But we have discussed that adding this noise can act like a regularization effect. We have discussed this under the Gaussian assumption. Remember a while ago, under the Gaussian assumption, I think I derived the connection. under Gaussian assumption, it was in one of the questions. The noise has an effect, regularization factor effect. Doing a noisy estimate is almost same as adding a regularization, L2 regularization factor to your objective function. So therefore, small batches can be appealing. They are appealing both due to their regularization effect and computational advantage, because they make things go faster. So for example, Keras fixed it to batch size to 32. That's the default value for Keras batch size. I don't know what TensorFlow does, but 32 is a small number if you think about it. The data sets are pretty big compared to the thousands of samples of the data sets. 32, you take only 32 random samples out of the data set and then use that to do your gradient estimation and use it in the gradient estimation. That's a pretty noisy gradient. So your gradient is pretty noisy. So that has a regularizing effect, as we discussed from a regularization point of view. All right, so I also try to put some interesting links to the slides. If you have time, you can click optionally. And some of the discussion here is quite directly from the deep learning book, because you cannot find much about this in Bishop. Classical books don't have that practical view of deep learning. So the only book that has some deep learning is actually the popular deep learning book of Bangio and so on. That you know already. So that has some practical discussions. Any questions? So you have experienced this little bit in your neural network training. You played with the batch sizes. I will go deeper after the break.
One question. So the weights are updated, like you perform the back propagation at the end of a mini batch or an epoch?
Mini batch.
Okay. So in one epoch, depending on the batch size, you might update the weights many times.
Actually, you're free to do whatever you want, but the mini batch gives you the gradient estimate. So yes, after you have a gradient estimate, you can only do one iteration of your gradient algorithm, right? So you update the theta t plus 1. So that's why it's called iteration, theta t plus 1, theta t plus the gradient with respect to theta. That gradient is estimated using the mini batch. And then you do, but because you're doing random sampling, you do multiple iterations. You're not doing a non-overlapping, right? So every time you're randomly sampling, and I think it's sampling with replacements. So essentially, you may end up using the similar samples. When I said 100 is divided, let's say I said the batch size is 32, and then your data set is like, say, I don't know, 128. There would be ideally like four of the mini batches, but you are not chopping it like you do in cross-validation. You are just randomly sampling 32 out of 128. And then in the next round iteration, you also take another 32. You're not making necessarily sure that they are not overlapping. So, but because of the randomness, they will be asymptotically you try all of the data points.
So the point of using mini batches is to make it computationally more efficient?
Computationally more efficient, and because that's the main thing. As I was saying, if you use the whole data set every time, you're in big trouble in terms of computation. And the second thing is people also realize, when I do this, I get noisy estimates. Noisy estimates are nicely regularizing effect. Regularizing is something I want anyway, so it works out kind of nicely. So it's kind of standard methodology these days. Yep, thanks for the good questions. All right, so let's give a break until maybe 1/4 and then continue with the stochastic training algorithms. Essentially the same topic.
Just wanted to ask you, here it says scale does not satisfy triangular inequality.
It doesn't.
But what do you mean by that exactly?
It's triangular inequality
Is that
is the
so?
metric. The triangle that we did in the back in the clustering, for example, when we were discussing the metrics.
Okay.
So you have the clustering slides.
Yep.
maybe in the unsupervised. I was talking about metric, distance metrics here.
Yeah, that's not magic.
But then, that's the similarity. I think the solution of this problem, there is this. This is the triangle inequality, right?
Okay.
Like a plus b less than
That
equal
should be
to.
the less than.
Yeah. A minus b less than equal to. Yeah.
And there was one more thing. I think there's a mistake. I'm not really sure. Oh yeah. This should.
Oh yeah. Where is that? People keep telling me. Is it in the slides?
Yeah, it's in the slide set.
Yeah, let's correct it immediately because I
Backpropagation
forgot.
gradient optimization.
Yeah. This. Oh, this is a.
Simple gradient.
But then I think I have not formulated it on this computer. So, I cannot. Now the formulator. I need to do this. So,
it's
okay,
image.
I'll try to. It's not an image, but yeah, I have it in my office computer.
Okay. And when we solved this problem last week, for find the forward propagation errors equations.
Back propagation.
No, forward propagation equations. You
Yeah,
remember
forward.
we wrote,
Yeah, forward. Yeah.
Why didn't we add the bias term, like when we wrote the equation?
The bias actually can be embedded to the weights, so everyone ignores the bias.
Okay, you just ignore that.
Yeah, ignore it because there's a way of embedding the bias into it.
Okay. And
So, like, actually, the non-biased version is good enough.
okay. And today when we did like regularization, it said batch size. If you decrease batch size, it acts like regularization, right?
Because of the noise. We had a problem
Yeah,
solving it.
but if we add another regularizer like this L2 on top of a small.
Yeah, but stronger regularizer.
Yeah, but is there ever a chance that it gives worse results than the normal?
Yeah, I mean, you can also overdo it. You can actually, while trying to do not overfitting, you can underfit.
That's what happened when I was doing my lab.
Yeah, you can do underfit, yeah.
So I was like, regularization is like, am I doing something
But
too much?
is your model too simple? Then it also
Yeah,
underfits.
Okay.
So did you?
Yeah, mine was a very simple model, like one layer and.
But how many did you have in there?
I put 8.
So that might be underfitting because your model is not expressive enough.
Okay. But then.
Then you need more model complexity. Just like think of it like these curve fitting with the polynomials. You may need more degrees.
Okay, I was just looking at Stack Exchange and seeing how to choose the number of layers and number of models, and they were like to prevent overfitting, just choose average of number of inputs and number of outputs as the number of new.
People have a lot of urban myths. Their own.
So we can go any number of layers and any number.
Yeah, but you can overdo it very easily.
Okay.
You can think of it like this polynomial fitting.
Okay.
You can do a quadratic, third degree, fourth degree, fifth degree. You can also do 50-degree polynomial.
Okay. Yeah, that will approximate it better. So,
But then
then
if then it will overfit.
It won't meet the training test data. So,
Yeah, it will overfit.
So we.
Then you need to regularize heavily. You can actually do big model and then heavy regularization.
Okay.
That will come back to some extent with dropouts and stuff.
Okay.
But then the best is choosing somewhere middle model and then doing the bit of regularization.
Okay.
There is no single
So
answer.
just trial and error.
It's a bit of art. I was
Okay.
saying there is an art factor to it.
Okay, so it's trial and error. You just do it and.
Yeah, that's
when
why
you get
everyone talks about it, and there's no conclusion, right? I mean, there's no.
a method or something.
Also, it depends on your problem.
Okay.
Like the complexity of the data dictates the complexity of the model
Okay.
and the properties of the data. Because at the end, you're trying to encode the data to your weights. And just think about this is also data dependent. Something that works well for one data set may not work well for other data. So this is.
Definitely.
And
And then there was another question with the two sigmoids. You said two binary include 4 classes.
I was going to do one more thing. What was it? This
This
one?
was WN.
But then there was one more thing that you were saying.
No, that was all right. the bias terms now that we did.
Ah, bias. Bias, example. Next year maybe. There's actually an example that shows actually you can embed the bias. Yeah, there's a way of embedding the bias in.
Okay,
So-
and then if we instead of using two sigmoids, we can use just softmax, right? As an application for that.
Yeah, yeah,
So 4 classes.
you can. It's up to you.
Is that easier or?
I don't know. Multiple inputs are also okay.
Okay. Because that is typically like giving 7 inputs and getting 4 outputs.
That's also fine.
Okay.
Then you choose the max out of them. So essentially you do the max afterwards.
Yeah.
Yeah, well, you need to try and see which one works best. It's a bit of, again, trial and error.
All right. Thank you.
Yep. Oh, battery run out. Oh, great. All right. Battery run out, so we'll use the mics on the desk. So it should still work out, I guess. Okay, I think we can start. Everybody's sitting, boring, getting bored. We discussed the batches and iterations and epochs. That's the standard terminology used by the popular libraries like Keras and TensorFlow. I don't know others, they use the same or not. There's PyTorch and other less popular ones. But some people, everyone likes their own library, favorite library. Let's look at the specifics of the stochastic gradient descent algorithms. I've been talking about, gradient algorithm, right? So we know that we use gradient algorithm to train the neural network, and we also know that we use backpropagation to find the specific gradients, but we also know that, if we use the whole data set, then we are in a bit of trouble. Therefore, we use these mini batch methods to do an empirical estimation of the gradient, and then which brings us to stochastic optimization, because we are doing a expectation of a stochastic variable in this case because of the sampling, and then we have this set of stochastic gradient descent algorithms and variants. They are the state of the art as of these days, years, for DNN, deep neural network training, right? So this is one thing you should be kind of mindful about. I should give you this pointer, it's important. When you read Bishop or older books from 90s on neural networks, their approach and then the perspective is quite different from modern deep learning books and, like the deep learning book. So, I always say in my communication network subject, we live in the internet time. That means, in the online world, time is up to 5 to 10 times faster. So 10 years is like 100 years when it comes to, computing. So things move very, very fast. That means you should check the date of your resource. And if it's from 90s resource, you need to treat it as a historical record. And you should trust those older books for the fundamentals, because they do an excellent treatment of the fundamentals. That's why I use Bishop's book, which is a classic. Deserves the name classic, but classic also means a bit old. I wouldn't go to Bishop's book for any deep learning stuff, right? I would go there to learn the fundamentals. There are many books like that. I use them to teach you fundamentals. But then the practical experience, how you do deep learning, I go to the most recent, there's the only book, deep learning book. And then I go to more, online resources. I put, despite they are imperfect, they are the only game in town. I don't want to give you, research papers that can be hard to read. So instead I linked to blog posts and so on that seemed reasonable enough to me, despite being imperfect. So, so that's the story when it comes to the resources and learning this stuff. It's a bit tricky because of the fast-moving nature, and things that are like 10-year, 15-year-old are already archaic. And then you should only go to those for the fundamentals. Okay? So the stochastic gradients, so in that sense, this is the very state of the art, is stochastic gradient descents and variants. Not just SGD. I'm not saying SGD is the most powerful one, but it's variants and the variations of the main idea. They are widely used for the training. So training, when I say training, of course, finding the weights of the neural network through the data set. So, you need to fix a learning rate and some require an initial parameter. This is very important. It's a non-convex problem. Where you start matters. When you descend in that landscape, I showed you it's a very hidden landscape. If you start somewhere, you get a different result. If you start somewhere else, you get a different result. This is direct implications. When you run the algorithm, initial conditions given by Keras actually matter a lot. They try to use library. People who create those libraries do their best to choose sensible defaults, initial conditions. But, you may want to mess up with that because, if you choose a wrong initial condition, the same network that was working before may not work because you're starting from a very different place, and then you're starting from a wrong place. Your journey to find the good one may be so long that you may not reach it in a practical limitations of your computer. So it really matters a lot, the initial parameter choices, initial conditions. So the loop is very simple. While stopping criterion is not met, this is the same stopping business as in a gradient descent algorithm in convex optimization we discussed. What do? We do this sampling the mini batch, right, of m examples from the training set. Here you go, with the corresponding targets, classification or regression doesn't matter. And then we compute the gradient estimate, with the batch. And then we do this update and then end it. So this is as simple as it gets. So this epsilon is the learning rate. And then learning rate, as we were discussing also, I asked it in the mid-semester test, you can have fixed, you can have diminishing, and then you can have also these line search methods. Line search methods are quite expensive usually. So what people do is like I wanted to put this additional small note there. You decrease it linearly, for example, you do a nice decreasing rate. You don't decrease epsilon over n, but you do it in a different curve decrease here. And then this satisfies our conditions, sufficient conditions for step size. Again, back from convex optimization, it needs to add up to infinity, and square is less than infinity. So therefore, this is a proper step size that will give me the solution, right? So that's the stochastic gradient descent method as we discussed, stochastic variant of the gradient descent, and with a bit of fancier step size selection, diminishing step size. But notice that this is not line search. This is also predetermined. It's done in a fancy way. It's not a linear decrease, it's a fancy decrease, but still it's predetermined. Next is as people actually, especially when the grade, because it's a very hidden landscape. In some localities of that landscape, if you compute the local Hessian's condition may not be good, right? So when you do it locally, it may look like convex in a locality, but its Hessian may not be good. Its condition of the Hessian may not be good, so it may be ill-conditioned locally. So people have, if you have high curvatures, so small gradients or noisy gradients, as we have the case, this goes back to 60s, by the way. This is a very, very old idea, momentum in optimization. So people said, I shouldn't trust the gradient that much. Actually, I should use this momentum idea from physics, like the same as the physics momentum, where mass times velocity, right? The car goes on the freeway, it has a momentum. You cannot stop immediately, right? So the same idea applied here. So what you do is the black ones are the gradients, right? The black ones are the gradients at these points, but you don't do the gradient. You kind of use the previous gradient and keep the momentum of that previous one instead of using the local gradient blindly, locally. That's the standard gradient algorithm, just uses the gradient. You go a step, then with the gradient estimate, you go another step, right? So that's what you do in the regular version. What you do here is actually you keep track of a momentum term, here V, right? So then you do a update of V, so you don't change your direction that fast. So you have a momentum going on, you go to the next step, you want to continue with that momentum despite the gradient now points to another direction. You actually find a middle way as shown here. So you keep track of that state V, momentum state, and update it with an alpha. You start to forget the previous one and then introduce the new one, which is the current gradient estimate, stochastic gradient estimate. That comes with its own step size and everything, right? So this gives you the new momentum. So you kind of, if I am going this way and the next step I'm here, I don't continue blindly that way because then I will end up in the wrong place because I keep using the previous gradient. The new gradient maybe points this way. I was going this way. I kind of go somewhere in the middle, right? That's the whole story going on with these equations, and very nicely shown pictorially, right? So this was going this way, then the gradient shows, black this way, but when you combine these two vectors, you end up this, then this goes this way, then again, it was going, the gradient, maybe the momentum is pointing this way, and then your current gradient pointing this way, so you kind of do a sum of those, the combination of those two things, and then once you find the V, actually you go in the direction of V, not the direction of your local gradient estimate. So you end up with this red path, which works better, and it overcomes the poor conditioning of the local Hessian matrix. When I say local Hessian, because it's not convex, the Hessian changes, right? So there is no unique, it's not quadratic. In the quadratic case, you have a unique Hessian that holds everywhere. In the other case, you have the Hessian matrix depending on where you are. So if it looks like a long, narrow valley or a canyon with the steep sides, the cost function has these strange shapes where the gradient doesn't give you enough information to move fast forward, then this momentum can save the day and kind of make you move forward quicker. So it's a practical thing. So once you have this idea in mind, what you do is naturally you incorporate this to your stochastic method, and then you get, for example, SGD with momentum, right? Stochastic gradient descent with momentum. In that case, it's the same story, but like when you do the gradient estimate, you do the gradient estimate with your mini batch, but then you don't use that directly. You do the velocity update. The V is velocity, okay? They call it velocity for some reason. So the velocity is what was happening before, keeping the state of the direction, and updates it with the most current update in a kind of a mixture sense, and then you go to the direction of this velocity. So that's the SGD with momentum. There are other methods that are based on the same idea. There's the Nesterov momentum. Nesterov is a good mathematician, an expert in optimization. He has done very good work in convex optimization. The idea is, of course, all these methods, although they are non-convex optimization, they are applied to non-convex optimization problems. They start from convex optimization ideas and apply them. So there's the Nesterov momentum that is a bit of a variant of the momentum. Then there is this other class of algorithms that use adaptive learning rates. Adaptive learning rates is not line search, but it's also not fixed step size. The learning rate, which is this kind of another name for step size in this case, is because the step size of the optimization changes your weight parameters, and so you are learning them in quotes. So therefore, the name learning rate. You can actually scale them inversely proportional to the function of the gradient. So how am I going to change my step size? They come up with these tricks, bag of tricks essentially, to make them proportional to the function of the gradient. Then when my gradient decreases, that means I'm closer to the that's an indication, observer of being closer to the solution. Therefore, maybe I should decrease my step size. So they create all these proportionalities, and there are a bunch of them: Adagrad, RMS prop, EDAM, and then their Nesterov momentum variants. There are all these different optimizers that are available, and possible to use. Because the projects are open source, actually you can go to Keras, and from Keras you can click from the documentation, it's one click away to the source, and you will see in the source, essentially these algorithms are coded directly in the source. You can see the Python source directly. So, there's nothing mysterious going on here. So you can read about the algorithm, and then actually I want to show maybe. I was going to list all of them, but I decided not to, because most of them are heuristics, and people came up with these variants, kind of designed them, and then tried the designs, and if it works, then it became popular. So the Wikipedia article is pretty good, actually. The extensions for stochastic gradient descent. So you get these all Adagrad, for example. There's this whole gradient, then there is the updates that are done in a certain way. Then the root means there is the adaptive gradient algorithm, then there is the root mean square propagation. So you see they keep track of some gradient state, then they change the learning rate. You see the learning rate here is changing in front of the gradient. Adaptive moment estimation, so it keeps multiple states, then creates combination of these multiple states to kind of do this parameter update. In this case, the V's or omegas are the parameters, weights that are getting updated. So you can actually look at these, and then as I was saying, going through Keras, should we click it or not? Maybe we should click it to the documentation. So maybe I should show this. Well, when you go to the optimizers, right, the usage of optimizers are here. And actually, here's the link that I was talking about. So SGD, stochastic gradient is here. The others are here. Ada delta, then Adam, optimizer. Actually pretty good because it also links to the book, the paper. So if you want to read about that, the original paper people came up with, this is the archive link to the paper. You can go read the paper, or you can go to the, let me show you, right? So if you want to do it the right way, so this is the paper apparently from 2014 by these authors. PDF is here, so you can sit down and read the paper that introduced this variant of stochastic optimization. And then for the Keras, you can actually take this and I open a new tab, the source, right? So this is the Adam optimizer. Default parameters follow those provided in the original paper. Okay, so you need to check the original paper in addition to the source. Here's the arguments, and then there's this a class init, and you get the get updates. You see even the parameter names are MS, VS. Then you do the optimization here, so, right? Returns the updates. So takes the as input as a function with the input. Yeah, init gets the different parameters, learning rate, beta, etc. And then it gives you the updates themselves. Here you go. So as I was saying, pretty open. So you can actually know the method. Your favorite library, if it's an open source, you can see the source. And then the source also, if it's well documented, then there's a nice link to the paper. You can go read the paper, which has an algorithm, all done, right? So nice package in terms of accessing information. All right. Last word is, it's a hot topic. It's this whole training the deep neural networks is a hot topic because people don't know as much about it as we should, right? So a lot of open questions, that's what I mean. It's a difficult problem. It's a non-convex, high-dimensional optimization problem. High-dimensional because the data sets are high-dimensional, the problems are high-dimensional. And then it's non-convex, it's messy. It's not nice ball shape where you go to the bottom of it like that. When you read Boyd's book, it's a beautiful, it's like a cartoon world, right? So you think of Boyd's book, the world that Boyd's book talks about is a cartoon world. Everything has a nice ball shape. You go to the bottom, everything is provable, right? And this is real world. It's messy and complicated and high-dimensional, and data is incomplete, and there's noise and everything. So when you want to solve real-world stuff, which actually these DNNs try to do, so training those and finding their weights from the data sets involves solving these nasty global optimization problems. And people have been speculating about them. For example, one of the main issues here is the saddle points between local minima. So one solution is here, one solution is here. The between these two is a saddle point, right? So if you start from here, so are you going to this way or are you going to this way? Or let's say you started from A and you found this local minimum. To find the other, maybe better solution, you need to overcome this saddle point. You see? So your algorithm should be able to do this additional stuff. And then how are you going to do that? You need to do some stochastic. Maybe you need to do a jump and choose another starting point, or these mini batch methods that help you make a noisy gradient, and then you make these noisy gradients are also useful because maybe they make you jump in the other way and help with the exploration, right? So this, when you have a landscape like this with many local minima that have ridges between them, the classical way is simulated annealing. You find the local minimum, you do a random jump, you find another local minimum, you jump and find another local minimum, then you find the mean out of those local minima that you have collected. And everything is dictated by how much time you have. And the same thing here, training the neural network. If you spend forever, of course you can find the best solution, but who has that time? So even training with the best computer, you are computationally limited. It's very real life in that sense. So there are papers, I kind of linked here also papers from different interesting papers. Some people are optimistic, so they say these minima are not like these single, they are not bottom of valleys like this. Some people think, oh, they are actually connected together with valleys instead of distinct valleys like this. Some people say most of the interesting problems we have been working on, there is a connection between them. The matter is only just finding those, navigating those valleys like the river between a hilly landscape and then finding it. I don't know, like this is a bit of speculation. Usually these papers don't give a mathematical justification. They just talk about their experiences from certain data sets. You should be kind of mindful of that. It's an active research topic, a better understanding of how we do this. And then these are all dependent on specific data and problems. I think this is safe to say. I would like to emphasize this. But sometimes it's enough. Like if you're solving the problem, you solve the problem. An example is, everybody talks about it. I want to talk about it briefly too, the autonomous car driving business, right? So let's look at the problem, right? If you make the autonomous car drive as good as a human being, and actually if you do it a bit better than humans and end up killing less people on average, you're done. It's a bit like the chess game or Go game. If you make your computer beat every human being in the world, then your task is accomplished. Because then you have a computer that plays chess, right? So chess wins against Kasparov, end of the story. Does this mean this is the best chess place ever in the entire universe? No. It's just a performance, with respect to something. So people kill a lot of people on the streets while driving, normal people. So you get like, road toll, like this many dead, this many injured. Unfortunately, that's the fact of life. If you make a self-driving car that does it, half the damage, then you're done. You don't need the perfect. So that's a specific problem. That's what I'm trying to say. The loss landscape is very specific. And if you find a local minimum that is good enough, you're done. You may not have the perfect zero-kill, self-driving car, but that may not be necessary. So actually, there's this really nice theorem from optimization, has nothing to do with deep learning or machine learning. It's called free-lunch theorem. And I would like to give you that they have proven very interestingly for the discrete case, discrete optimization, a result that is very interesting. The result says, let's say you have a discrete optimization problem. Still, optimization is optimization. You try to find the minimum of something, right? What the no free lunch theorem says is, if you find an algorithm, first of all, it talks about, because it's discrete, you can actually easily describe all possible problems. Because this discrete and finite, there are only finitely many combinations. It may be a huge number of combinations, but it's still finite, okay? It's not infinite. So let's look at all possible optimization problems in a finite discrete setting. They actually in their paper define it nicely and easily. Therefore also it was difficult to kind of create a counterpart of that result for the infinite case. Because in infinite it is harder to show. And I don't think they have shown it properly. But even the discrete version gives you a lot of insights, I think. So you can create an optimization algorithm like some of the ones that we've been discussing, counterparts, and then it may work for some subset of all possible problems very well. Makes sense, right? So I found a nice algorithm. It solves a subset of the all possible problems very well. No free-lunch theorem says, that's where the trick is, it says, then this, your nice algorithm that worked well for subset A of the all problems will work worse than random for the remaining problems. That's very interesting. So in average, what it says is, on average, for all possible problems, you cannot do better than random search. That's a bit demoralizing. So if you say, I'm going to come up with an algorithm that solves all possible problems in my set, and it will do better than random search, they show that that's not possible. So if you do better in some parts, you will do worse than random in other parts. So that's why it's called no free lunch. So your gain, you work hard for lunch, but then you pay the price in other places. So I think that gives a nice insight if you take the extrapolation, which should or not should be taken, but I like to take it. So if you come up with a great algorithm that solves a class of trains a class of neural networks that solves a class of problems, that may be good enough. You may not need to do the best thing for all possible problems. And no free lunch theorem indicates, it doesn't prove, but indicates, because it proves only for the discrete case, indicates that maybe your algorithm will be worse than randomly doing something for other classes of problems. But as I was saying, if your problem class is well defined, then who cares? So that is kind of an insight one should add, maybe to the art of deep learning, something to keep in mind. Or that's my personal interpretation. I thought it will be useful to share with you, and you can come up with your interpretation after doing a lot of practical stuff. All right? So that's the story. So I kind of, also these learning objectives, I tried to highlight what is covered and as a guideline for study. So without further ado, and unless you have comments or questions, so we go to the sequential data, which is a very important topic. Especially as engineers, it is important because we live with dynamical systems and type of systems, and systems creates sequential data. So I will give the basics of sequential data analysis, then I will touch the Markov models. Actually, I can spend a lot of time on Markov models. There's beautiful math there, but I will not do it, to be honest. And then I will touch the linear models, and without too much yada yada, I want to come to recurrent neural networks, and because it was requested, initially I wasn't going to cover, but I'll also say a few things about CNNs as well. So there are extra resources for this. There is this open textbook that you can download, but there is also this classical textbook, Analysis of Time Series and Introduction, a really, really old Chatfield book that is highly recommended, and I kind of liked it. If you find it somewhere, you can check it. This one is already under your fingers, and the other relevant chapters are here. So, what is the difference? The difference is this. So until now, we have used the data sets, treated data sets as sets. A set is an ordered, elements. It's a bag of data points. So we kind of tap to the bag of data points. There's no order to them. All of the problems we looked at it was like this, right? So now we look at time series where data is ordered by time. There's a sequence to the data, right? And now, until now, because of the unordered nature, we could adopt a probabilistic worldview. There's an underlying joint distribution that generates these IID modeling assumptions. So we now consider sequential data, often comes from time series, as I mentioned, and then from systems. A lot of systems generate this data, economic systems, physical systems like weather. There's engineering systems, control, communication, power systems, signals. So there are a lot of engineering systems create, structured, time-structured data. Therefore, I think this time series data is very relevant to us engineers. And then event-based. Also, you can have a sequence of events like faults, security events, medical events, right? So your heartbeat is time series, but a sequence of illnesses or your measurements of your blood tests and so on. So there's this event-based things that may not be as regular as time, but from time to time. So I tried to put two examples here. So electricity use globally and in a state or at your house or in your neighborhood, all those different types of usage, energy demand, heating demand maybe. There's also this one is interesting. The hot topic is predictive maintenance. So you look at certain parameters of your engine or your device or your system, and then you observe different parameters of it, measure them over time, and then you try to predict will it fail or not. And if the probability of failure goes beyond a threshold, you say, oh, maybe it's time for maintenance, I should check this device, right? This makes a lot of sense. If you have limited resources, you cannot check all the devices all the time. You need to make choices, optimize your checking. Such predictive stuff, especially the complex nature of faults emerging, the machine learning methods have been promising. It's an emerging area. So objective of time series analysis is description and prediction. And what we do as methods for analyzing and predicting includes a lot of, this is a deep, fundamental topic. That means people have been looking at it forever. People have been looking forever means there are a lot of methods and literature piled up over the years and decades. So people look at it as filtering. You can filter the data, right? You can do a moving window low-pass filtering. People do that a lot for any trend to get the trends, get rid of the local noise, like in stock market and other things, house prices. You do a moving average of them, which is a low-pass filtering. If you have a dynamic system, you can do Kalman filters for estimation. Other nonlinear filters are also popular, but I won't have too much time to go to there. I will stay with the linear models there. Curve fitting, you can use actually curve fitting to estimate the next steps. Probabilistic models, Markov chains I'll talk about a little bit. Dynamical system, you can use system identification to get the dynamical system model, and then from the dynamical system model identify the time sequence. There's a whole system theory there in control theory and signal processing. And then neural networks I will talk about, right? So there is this mathematical, an important concept here is stationarity. And there is a very well-defined mathematical description of stationarity, but in the interest of time and not doing too much math, whenever I do math, a lot of people start to complain. So not to pile it up too much, I kind of skipped it, but you can actually go to your probability book and check the stationarity definition if it hasn't been done before. Has it been covered in probability random models? Stationarity, weak sense stationarity, and so on. So you already know it then actually I can assume as known knowledge. So the idea is that the underlying, just to refresh our memory, the underlying characteristics are remaining constant. Stationarity means the mean variance probability distribution, depending on how strong or how weak the stationarity assumption you are making, right? So even if it's not stationary, we can assume some stationarity over some limited time window. Even if things are changing, we can assume that we can choose a window small enough, and we can say, oh, over this window at least, it doesn't change that much. And then over bigger windows, it may, change a lot. Lack of, that's the idea. And then we need to make some stationarity assumption, because what I said, remember quite a while ago in supervised learning, you need to be able to, if the test set or future samples are disconnected from your training set, machine learning is not magic. If you train on a training set and existing data, right, then your test set and the future samples need to have similar characteristics, otherwise you will get it wrong. It's impossible to get it right. Nobody has a crystal ball. The same thing applies here. If you have a time series data, and if there is no stationarity window, the underlying characteristics keep changing, then that means if you train on what you have already, tomorrow everything has changed. So your training is worthless. It will not work, right? So therefore, stationarity, at least over some time window, is a necessary assumption, just like we did with the supervised learning. It's the same, it's a corollary to that. Actually, that's, this lack of stationarity is the cause why you cannot get rich in stock market with these methods unless you do high frequency trading. So you can actually use some, you can use a little bit of estimation, time series prediction, and you can play on the stock market. For short time windows, your maybe estimator will work well, but then in the long run, if you repeated the play, then you are playing over longer time windows, and then maybe some days you will gain and some days you will lose. On average, I expect it will not work because you will get unexpected events wiping out your stuff, portfolio. So only way where people make money is in my opinion, is high frequency trading. Why does it work? Keyword is windows. Exactly. The high frequency trading, they make money because it's such a small window that the market characteristics don't change over the next 1 second. No big events have time to propagate, so they buy and sell like crazy during that 1 second stationary window, and in that case, yeah, your algorithms may work. But it's a cheating and it should not be allowed, but that's a different discussion for finance people. But from prediction point of view, yeah, if you make the window small enough, it works, and that's exactly what high frequency trading people do. Right? I think maybe this is a good stopping point. So tomorrow I will finish this slide set. Then next week I will spend time on reinforcement learning. I will post the slides and the workshop for next week and the last week. So that will be also 2-week workshop 4, hopefully by Thursday or Friday latest. And then I think it's a nice workshop. I spent a lot of time this weekend on it. And then we will close off with reinforcement. There is a guest lecture at the end of the semester. I will announce it again for the LMS. Right? See you tomorrow.